The ability to perform the assessment of electromagnetic field density is an essential skill for any RF engineer, and especially for any EMC test engineer, which is very commonly associated with the task of evaluating electromagnetic field exposure of commercial products. The need for this assessment is driven by the ICNIRP guidelines that apply to radio transmitters between 0 and 300 GHz and apply globally. In this video, I'm going to show you how to perform this assessment on an LTE modem designed by Telit. It is going to be the LE910C4 LTE modem, and I'm going to use a commercial off-the-shelf antenna designed by Abracom as an example. We're not going to need to perform any measurement, we're just going to perform calculation, and I will explain why we don't need to perform any measurement as well. Before we begin this assessment, let's take a look at the limits that we need to comply with. And in the European Union, the main regulation that we need to assess against is the EN Council Recommendation 99/519/AC, which specifies the limits of electromagnetic field exposure for general public areas. We also have a similar directive, 2013/35/EU, that applies limits for worker areas, or in other words, the areas where the workers are expected to wear personal protective equipment against electromagnetic field exposure. So basically those would be the telecommunication site areas with restricted access, where only workers with special permits are allowed. And as we can see from this table, besides the electromagnetic power density, we also need to calculate the electric field strength, magnetic field strength, and the magnetic flux density. But as we know from the Maxwell's equations, all of those things are closely linked to one another and can be calculated effectively with the same formula. Let's also take a closer look at the device under test. And as I said, this is the Telit LE910C4 module that is basically LTE module that can transmit several bands, and we are going to use this antenna that is designed by Abracom, and according to its data sheets, the modem has a transmit power level of 22.5 dBm, and the antenna has 2.0 dBi gain. Important parameter we can extract from this data sheet of the antenna is the length of the antenna, which, as you can see in this case, is 67.4 millimeters, and this is going to be our D, which is going to use for the calculation of near field distance. So these are effectively the main parameters that we need to extract from the data sheets of this antenna and the modem. If I had a longer cable than this one, I may also want to include the power loss in this cable. However, since this cable is very short, I'm not going to include it in the calculation. The near field distance of the antenna is important because it's going to determine which formula we need to use for the calculation of electromagnetic power density. And this relationship is defined in the EN 62311 2008 standard. This standard specifies several ways in which the assessment of electromagnetic field exposure can be performed. However, the main takeaways for us from this standard are going to be the calculation of the near field distance, which is actually described in its appendix, and it is the appendix A we need to look at. The Annex A of EN 62311 standard contains the formulas that we need to use for the calculation of electromagnetic power density for all regions in front of the antenna. And as you know, there are three main regions that we need to consider, and you can listen to my other video on this topic, but in summary, those are the reactive near field, which is effectively the distance directly in front of this antenna, and then there is a radiating near field, which is effectively lambda over 4 area, and we also then have the far field, which is the 2d squared over lambda, and the d is the maximum dimension of the antenna, which, as I have showed you from the datasheet, is going to be the length of the antenna, and sometimes we can also consider the diagonal or the diameter of the antenna, but in this example the length is enough, and this is going to be basically 68 millimeters. So if we go back to the standard, we can see that the power density S is effectively the cross product of electric and magnetic fields, as we know from Maxwell's equations, which also equals to P, which is the transmit power, and P is equal to average power multiplied by the duty cycle divided over 4 pi r squared, where r squared is the distance to the receiver. Then if we scroll down, we will also see the definition of the radiating near field region, which is characterized by lambda over 4, and also the reactive near field region, which is less than lambda over 4. And the reactive near field region, as you can see, is really quite challenging to calculate, but we don't normally need to do this kind of calculation. However, if you ever needed to, this standard is exactly where you will find what you need to do. The other thing that I should mention is that for any device that is expected to be used in closer proximity than 20 centimeters from human head or body, we must also perform specific absorption rate test. And this is a different test, and that we cannot just calculate. We actually have to go inside an anechoic chamber and use this probe that will poke a mannequin filled with water at different places and measure the power density. This definition actually comes from another standard called EN 50665 that will tell us that if a device is used for longer than 6 minutes in front of a human head or body, then the SIR testing needs to be performed, because this now becomes the normal operating condition for this device. However, if a user only comes in close proximity of a radiating antenna sporadically and doesn't stay for longer than 6 minutes, then the calculation of electromagnetic power density is also an acceptable way of satisfying the EMF requirements. Now let's begin the assessment. First of all, let's calculate the far field distance from the antenna, and for this I'm going to use the highest frequency of my device, which is going to be the LTE band 1 frequency, and that frequency is equal to 1920 megahertz. So LTE 1. So, and the reason I'm using the highest frequency, because this is going to give me the largest distance. Well, but why is this correct, you may ask? Isn't this the opposite, that the largest frequency is going to give you the shortest wavelength and the lowest frequency is going to give you the largest wavelength? That is true. However, in our case, the largest antenna dimension is going to be the same for all frequencies. And as we figured out from the antenna datasheet, D is equal to 68 millimeters. And this distance D is now going to dominate the far-field boundary, which is defined by the formula 2D squared over wavelength. And even though the wavelength is indeed shorter at larger frequencies, the largest D is going to give us the largest R. And for the band 1, the wavelength is going to be equal to C over F, which is the speed of light, over the frequency of the carrier transmitter, which is 1920 megahertz. And this is going to be approximately equal to 0.156 meter. So now we know everything that we need to calculate the far-field region, and this distance is going to be equal to approximately 0.108 meter. So as you can see from this number, this is smaller than the required number for the SIR method assessment, which is 0.2 meters, in other words 20 centimeters. So that means that we are always going to be in the far field when we do the power density assessment. So we can begin the calculation of the power density field in accordance with Annex A of EN 62311 standard, and as well as Maxwell's equations. We can start by writing it out. Then the power density S is equal to the cross product of electric field with magnetic field. And then more specifically, it also means the P, or the transmit power, multiplied by gain and divided by 4 pi times R squared. I should also differentiate between the cross product and multiplication, because in this case this is a multiplication and in this case it is a cross product. So this is the formula we're going to use, and we can also take from the datasheet G, which is the gain, and this is equal to 2.0 dBi, which, as I mentioned, is an isotropic gain of the antenna. Then the power P is actually equal to power average multiplied by duty cycle. Now, if we look at the datasheet of the Telit modem, we will see that the duty cycle for LTE band 1 is 100%, so that just means 1, and the average power is 22.5 dBm, so basically that is 22.5 dBm is the actual P that we're going to use in this formula. However, for other bands, especially GSM, you have to use a different value for duty cycle, so you should be careful about this, because it can be 12.5% rather than 100%, but then your peak or average transmit power will be significantly larger as well. But here comes the tricky part. We have power expressed in dBms, but our gain is expressed in dBis, and according to the formula we need to multiply them. So how are we going to do that? So first of all, we need to convert dBms into dB watts, and 1 dB watt is equal to minus 30 dBm. In other words, we can simply extract 30 from our dBm value, and then we will obtain our power in dB watts as 22.5 minus 30 equal to minus 7.5. Now we can add our final gain and obtain the top part of our equation, which is going to be minus 7.5 plus 2 and equal to 5.5 dB watt. So this is effectively the tricky part, because now we need to convert all those values into the right format. So, and the formula we need to use for conversion to watts is equal to 1 watt times 10 times power in dBm over 10 over 1000. So first of all, we're going to obtain back our value in dBms, and this is going to be equal to 24.5 dBm, and then we can insert the dBm into this formula, and we're going to obtain the value of 0.28 watt. So this is effectively our value that we're going to insert into this formula. So this is for the top part of this equation. This is now equal to 0.28. And then we're just going to divide it by 4 pi times r squared. P plus gi over 4 pi times r squared is equal to 0.28 watt over 4 pi times 0.04. So this is because our r is equal 0.2. In other words, 20 centimeters. In other words, we are evaluating electromagnetic power density at the SAR distance, which is the highest distance that is allowed for us to the user until we need to do SAR measurement. So when we perform this calculation, we will obtain the value of 0.55 watt per meter. And this is going to be the final answer for S. So this is what S is equal to under the far field conditions. Now, you may ask what is the limit, and according to ICNIRP guidelines, the limit is actually at LT band 1 is equal to 9.6 watt per meter squared, actually. And that is true as well. So there you go, we are significantly below the limit for this carrier frequency, and that as a carrier frequency we're only going to get lower values than this, because they will have a smaller far field region. So this is the limit. Now, based on the power density that we have calculated, we can now also calculate the magnetic field, electric field, and the magnetic flux. And I will show you exactly how. While the relationship between electromagnetic power density and electric and magnetic fields comes from Maxwell's equations, the magnetic flux density, we need to calculate based on constitutive parameters. So there are two things that we know from the constitutive relationships that will help us here, and those are that, first of all, the impedance of free space, or in other words of air, is equal to 377 ohm. I should probably write approximately equal to 377 ohm. And the other constitutive parameter that we'll need is the permeability of free space, and that is equal to 4 pi times 10 to the power minus 7 h per meter. And h stands for henries. So this is effectively all that we need to know from constitutive parameters. And now we can write the remaining equations as follows. So S is first of all equals to electric field over impedance of free space, and by the extension it also equals to the cross product of free space with the square of magnetic field. So now you have it. This is how we can figure out electric and magnetic fields. And by the way, these are all vectors, so we can include this in our calculations as the way of writing those equations properly. So based on that, we can now calculate electric and magnetic fields according to this formula. So effectively E is going to be equal to 0.55 over 377, and I keep doing this, but this is approximately equal to, and so now if we divide 0.55 watt over 377, we're going to obtain the value of 0.0014, but remember that this is the power density that is expressed in watts per meter squared, and now we're trying to obtain electric field value, which is volts per meter. That effectively means that we need to multiply this value by 10,000. So, and that is now going to give us the value of 14 volts per meter. That is the actual answer for electric field intensity. So now we can also calculate the magnetic field intensity in accordance with the same formula, and that is going to be expressed as H, and it will be approximately equal to 0.038 amps per meter. So there you have it. We have now obtained the electric field intensity and the magnetic field intensity from the electromagnetic power density. And the last equation that I'm going to share with you today is going to be the calculation of B, which is the magnetic flux density. And magnetic flux density B is equal to permeability of free space multiplied by H. The unit of measure for B is Tesla, but because this value is going to be extremely small, we're going to express it in microteslas, and this is going to be approximately equal to 0.048 microtesla. So this is the unit of measurement. So as you can see, we have now expressed all our key ingredients of Maxwell's equations based on electromagnetic power density. So this is really the key to the calculation of any of these, and we can now compare all those values against our limits from ICNIRP tables, and we will find that they're significantly below them. So you can now see the entirety of the calculations that we performed today. So first of all, we established where the far field distance is and whether or not we can apply the far field formula. So we can, then we applied it, and then we converted from different units of measures from dBms to dB watts to obtain the power in watts. And then we used the power density formula to obtain the value in watts per meter squared, which was below the ICNIRP limit. And based on that, we also been able to calculate electric field density, magnetic field density, and magnetic flux densities, which is all based on Maxwell's equations and constitutive relationships. So this is effectively how you can perform this assessment, and the last thing you would do, you would write it all out in some sort of a table. So you would say it's like that. And then you effectively compare it against the limits from ICNIRP guidelines. So if we look at the ICNIRP guidelines, we can figure out the limits for band 1 of LTE, and effectively those are the limits for the power density, which is 9.6 watt per meter squared. We were significantly below that. Then we have the limit of 0.16 amp per meter. Again, we were significantly below that. We have a limit of 60.25 volts per meter at this frequency. So as a reminder, this frequency is 1920 megahertz. And finally, we also have a limit for the magnetic flux density equal to 0.2. So all those limits are frequency dependent, as you can see, so you also need to calculate them. And as you can see, we were significantly below all of our limits, and we passed this assessment successfully. So this is everything that I wanted to cover in this video. It became quite long as usual because all of those topics are quite challenging to explain, but I hope it's been very practical and you can take away this knowledge and apply it in your company, in your products, and basically figure out if you comply with the regulatory limits for electromagnetic field exposure, or you can equally use it for any other magnetic or electromagnetic power density calculation which you may need to perform to assess the performance of your antenna arrays and such. So please like and subscribe the channel, and I hope you enjoyed this video. I'll see you very soon.